Hey everybody, Shane from Norman S. Wright. In last week's video, we talked about sizing water coils at altitude. This week, I want to talk about selecting fans at altitudes. So let's get started. A couple videos back, I discussed how a cubic foot of air at sea level is the same size as a cubic foot of air in the mountains. So 1 CFM in Dallas is the same volume as 1 CFM in Denver. But because Dallas is at a lower altitude, that cubic foot of air is denser. It has more molecules packed into it. And last week I discussed how lower density air has lower heat transferability because it has lower mass. So let's move this up. What does lower mass mean for fan selections? A fan is a constant volume device, meaning that at a given rotational speed, it will move a specific volume of air. If I draw a forward curved fan wheel, and let's say each of these blades can hold a cubic foot of fluid, because air is a fluid after all, if it takes a minute to go one full rotation of the wheel, that would be 1 revolution per minute, or RPM, and since there are 6 blades, that would move 6 cubic feet per minute at 1 RPM. If instead of air we had water, it would still also move 6 CFM. Make a little bit of room. But you can imagine that it would be harder to move the water compared to the air because it's denser and has more mass. So let's move this up. This is exactly what happens with air at different altitudes. So at high altitudes, you need lower horsepower to rotate a fan at any given RPM compared to the same fan at sea level. Static pressure is also affected by altitude. At high altitudes, there's less mass to the air. A given CFM of airflow will generate less static pressure too. Let's move this up. If I go back to my rock and feathers example from a few videos ago, it's easy to imagine that the cubic foot of rocks will put more pressure on you than the cubic foot of feathers, if, say, someone put it on your foot. So even though the fan moves the same volume, the mass of that volume changes, and that's what drives the horsepower and static pressure differences. So let's move this over. Since catalog data is shown for standard air, which, as a reminder, is dry air at 70 degrees Fahrenheit at sea level and has a density of 0.075 pounds per cubic foot, how do you select a fan if it's going to operate at altitude? There are catalog correction factor tables for various temperatures and altitudes, so let's make some room and pull one up. In the actual building, the required static pressure hasn't changed. You're just converting it for the catalog curve, which assumes denser air. So you can see here that if you go to 70 degrees and 6,000 feet, the correction factor is 1.25. So let's move this up and let me pull up a fan curve. You have static pressure over here and CFM down at the bottom, and each fan curve line represents different RPMs. So let's say you need your fan to generate 1.5 inches of static pressure at 5,000 CFM, and that puts you right here on the cataloged fan curve, which is at 1074 RPM. Let me erase these circles to make it a little less confusing. If you select your fan at 1.5 inches on this curve, which assumes standard air, your actual static pressure would be lower because of the difference in density. So we need to use the correction factor. So we need to multiply our 1.5 inch pressure by 1.25, which gives us 1.875 inches. And we need to look at the cataloged fan performance data at 1.875 inches. So at 1.5 inches and 5,000 CFM, we're at 1074 RPM. And at 1.875 inches and 5,000 CFM, we're around the 1134 RPM curve. So remember that 1.875 is the standard air density equivalent static pressure at your altitude. Okay, let me make some room. So now we know that we'll need to operate this fan at 1134 RPM to get the static pressure and airflow we need. Now let's look at horsepower. The actual brake horsepower you need is equal to the air density ratio times the standard air brake horsepower. The air density ratio is the actual density divided by the density of standard air, and at 6,000 feet and 70 degrees, it's about 0.8. My example curve here doesn't have brake horsepower on it, so let me just draw it in for our example. So let's look at our brake horsepower curve, and you can see that we need, we'll call it 2.5 brake horsepower at standard air density. So 2.5 times 0.8 equals 2.0 brake horsepower at our altitude. This means the motor will draw less horsepower at altitude because the air has less mass to move. Let's move this up a little. So even though the fan needs less horsepower at altitude, you must still select the fan using the corrected static pressure, which is higher on the catalog curve. And that's why both the static pressure correction and the brake horsepower correction matter. Let me make some more room. And this is not just for altitude. And if your application has higher temperature air, such as an industrial oven or furnace exhaust application, where you could have 300 to 500 degree air, you would also need to use the catalog correction tables to ensure the correct fan selection. So let's bring everything back on screen. Of course, you're most likely using selection software, in which case you just need to make sure you enter the altitude or temperature if it varies a lot from standard air. So that's how altitude and temperature affects fan operation and selection. If you have any questions or suggestions for future videos, put them in the comment section below. And don't forget to like and subscribe to our YouTube channel. Thanks for watching, and I'll see you next week.